So Jesper Jacobsen is going to give us his third talk on conformal field theory.
Okay. I don't know what happened to the audience, but anyway. So today I'm going to harvest the results of every bad thing that I have been doing to you for the last couple of days. So I just stopped yesterday, just before concluding on what this so-called uveal conformal field theory is, that will describe these loop models. And then the rest of today is dedicated to getting results. So the partition function was this functional integral, and there were three pieces in the action. One piece was just this Gaussian term, which controls the interface model of these heights, of which phi is the continuum limit. And there was this boundary term here, which gives the right weight to loops which wrap around a cylinder. And we have identified this now with this compactified boson conformal field theory. We have seen that there are operators which use electric and magnetic charges which live on mutually dual lattices, and the electric charges are the E's coming in here in these exponentials of the field, which are known as vertex operators in physics, and height defects, so screw dislocations in the height field, are magnetic charges. And
Jesper, could you just remind me what that script R of X is again?
Script, what?
In the
SV.
That's the scalar curvature,
scalar curve.
which I choose to take all the way out to the boundary using Gauss-Bonnet.
Right, okay, thanks.
And we know what the critical exponents are. So that's still a summary of yesterday. So we know what the central charge is. And E naught was my parameterization of the loop weight. And we know what these electromagnetic operators have as a scaling dimension. And the only thing that I haven't said anything about yet is how do I actually find the scaling limit of these loop weights, and how do I put that into the theory? And so that
E and M are integers?
And E and M are live on mutually dual lattices, and I believe that M must be a multiple of the fundamental height step, which I have chosen to be pi, but that was just a convention. Of course, everything can be normalized so that they are integers. But somehow, for historical reasons, people don't do that. Okay, so remember also that I had distributed out my loop weights as these complex exponentials. So the idea was that the loop weight was distributed out in two directions. And so whenever I took a certain turn through an angle alpha, then there was an exponential of plus minus I alpha chi over 2 pi associated with it. And so this last term in the action is just going to be the continuum limit of those microscopic vertex weights. And so now the crucial thing is that the microscopic vertex weights, of course, are periodic in the height, because what I had showed already was that if you just change your height by 2a, then you're going to get back the same microscopic configuration. So at the very least, I would expect this thing here to be periodic when I change phi by 2a, but actually it turns out it has a higher periodicity. So what I want to do is that I want to do Fourier analysis of this SL. So I want to write these weights here as a Fourier series. And what comes in here are then just those vertex operators, those complex exponentials. And now what you can do is that you can go through my little example before to sort of get a shortcut logic to find out what those e's should live on. And so it's already clear from what I said that at the very least this LW is a sublattice of the trivial lattice of integers. That is to say, if I go from here all the way to here, I'm getting back the same microscopic configuration, so at least it should be periodic under that. But if you see what happens when I go through here, well, here I've got only left turns on the first panel, and on the third panel, lo and behold, I have also got only left turns. So supposing that this is representative for finding out what this periodicity is, it will now seem that LW is twice L0. And you can work out more complicated examples and confirm that that is indeed the case. So now I know what this L is, as L is. And now comes the crucial physical argument, which solves the theory. So I have a model where loops can have all possible sizes. They can be very small or they can be very, very big. And to each loop I give the same weight n. So now usually in quantum field theory, one likes to think about things renormalizing when you see them on different scales. So in particle physics, people would say that the mass of some particle is something else on a small scale or on a large scale, so things renormalize. But here the microscopic model dictates me that loops should have the same weight irrespective of their size. So the operator which implements their weight should be exactly marginal under a scale transformation. And exactly marginal means that its scaling dimension is equal to the dimension of the space, that is 2. So in this expansion, in this Fourier series of SL, the most relevant operator, the one with the lowest scaling dimension, well, should have a scaling dimension of exactly 2. Once I impose that, the coupling constant is fixed. I just have to write out what this is using my formula for these electromagnetic scaling dimensions.
Sorry, just in your title line, RG, is that standing for
renormalization group?
Okay.
Right. Okay, so remember n was 2 cosine pi e naught. So now G is linked to n, and G was the thing which governed the elasticity of my interface. Of course, it might happen that the amplitude in front of that vertex operator vanishes. That would be a very exceptional situation, of course. That would require me to adjust some parameter in the theory. So what you could imagine would be that in the ON model, you remember that there were loops, but they didn't cover all of the lattice. There were some places where there were voids. So if I sort of adjust carefully the weight of those voids to some value, I could expect this to vanish, and then it would be the next most relevant operator which would come into play, and so on and so forth. And so in that case, I would take this choice here. So both cases are covered by the following. N, the weight of a loop in the ON model, or square root Q, the weight of a loop in the Potts model, should be equal to minus 2 cosine pi G, where G either lives in the range 0, 1 for the first case up here, or in the range 1, 2 for the second case here.
I'm sorry, but the second case, you mean either of the two subcases of the second?
Yes, right. Exactly. Okay, so now we are going to harvest. So we want to know something about critical exponents. So the first kind of critical exponents that I would like to deal with are exponents. Well, maybe the drawing could have been a little better. So I take 2 points, which are going to be far away. I have all my loops. All my oriented loops live somewhere. And in addition, I require that there be topological defects in these 2 points here, so that L-oriented lines come out of one point and go into the other point. And I want to know, so the partition function of that divided by the partition function without these defects is going to decay algebraically with the distance of these points. So I want to know what that algebraic decay is going to be like. That will define a critical exponent. Okay? And so you can see exactly what magnetic charges correspond to these thing here, because when I encircle this vertex here, I'm going to get a height dislocation, which is going to be L times the fundamental height step. And so I'll just evaluate the corresponding delta, but there is one subtlety. There's one subtlety coming from the thing here that I have these complex weight when things wind around. So, you know, it might happen, and at this insertion point, I'll just draw it here again. Suppose there's one line coming out and it does something like that before going over to the other point. Then it will pick up a lot of complex exponentials. I want this object here to be weighted by 1. It turns out that the cure is to insert an electric charge E naught here. So I arrive at this formula here. The scaling dimension that I want for these L legs to propagate is equal to delta of E naught and ML, where ML is this magnetic charge, and it's this. So that tells you a lot of things that I presume that you would like to know. So for one thing, if I put L equals to 2, it tells you what is going to be the fractal dimension of a 4-twin Castelline cluster. Simply because the fractal dimension of the boundary of a 4-twin Castelline cluster, because you can imagine marking 2 points on the boundary and having these 2 legs here wind around the cluster because they are cluster boundaries. And so the object that is going to come out here is just the codimension of the fractal dimension. So 2 minus delta 2 is equal to the fractal dimension of the boundary. So df the boundary is going to be 2 minus delta 2. And I can do something more. For example, this thing here with 4 legs coming out, what does that mean? Well, that is going to be the codimension of the fractal dimension of the set of isthmuses or bridges in the 4-twin Castelline cluster. For the following reason, suppose that you have a cluster which has a bridge. Well, then it means that its boundary will do something like this. So it's like 2 very close nearby points, which will spit out 4 legs. So I can mark these guys by having this construction with L equals 4. So then d fractal of bridges is going to be 2 minus delta 4. So I learn a lot about the geometry of 4-twin Castelline clusters in this way.
This has a particular connection to percolation, of course, when Q goes to 1, right?
Right.
And the issue of, fractal dimensions of surfaces or the quote-unquote volume of the percolation cluster.
Yes.
But you haven't set Q equal to 1 here, so.
Oh no, I mean it's valid.
So you have
it's valid for this the loop weight. So the loop weight was square root of Q, right? So that guy belongs to the interval between -2 and 2. So I could set it equal to 1 if you want. Then G would be 2/3. So you just put 2/3 in this formula.
So in particular, then you reproduce some known results on
Of
fractal
course.
dimensions and percolation.
Of course, so the fractal dimension of bridges in percolation would be 3/4, and the fractal dimension of the boundary would be 7/4. I haven't yet shown what the fractal dimension of a percolating cluster is. That's going to be something a little bit different, and let's turn to that next. But before doing that, let us just remark that these exponents that I have just found fit nicely into the CATS table of the minimal models. Let me get this little handle on the side. Remember, there was this index M for minimal models. I can identify it with these combinations of G, and it turns out then that delta L in the notation of this CATS table is equal to this. So they fit into this grid, except that somehow the first index, which was supposed to be an integer between 1 and M, has now become 0. So, well, anyway, that doesn't put up physicists. Okay, let's turn to the magnetic exponent in the Potts model. So the magnetic exponent in the Potts model for Q equals 1 is the codimension of the fractal dimension of a percolation cluster. For the following reason, the probability that two Potts spins are in the same state, you can easily check, is proportional to the probability that the 2 points belong to the same cluster. So they will decay with a common exponent algebraically. Okay, so what does it mean that 2 points belong to the same cluster? Well, suppose first that I'm on a cylinder. Of course, I can always transform things back into the plane by a conformal map. And let's suppose that x1 and x2 are widely separated points. And let's suppose that there is a cluster extending from one end to the other. Well, what does that mean? That means that there is no cluster boundary which will wind around the cylinder. Okay. So suppose I manipulated my theory a little bit so that I gave different weights to boundaries, so cycles which are homotopic to a point and those which are not. That is just possible by manipulating this SP term a little bit, and then I would put the weight of these guys equal to 0. So what I need to do is to insert these vertex operators here at the cylinder ends so that n bar is 2 cosine pi E1, and set E1 equal to 1/2 so that n bar is 0. And then I would have to compare the free energy of that to the free energy of the ground state, where E1 is equal to E0. So delta magnetic would be delta 1/2 0 minus delta E0 0, and I get this result here. So that's the magnetic exponent of the Potts model. And so in particular, that will prove to you that the dimension of a percolation cluster is 91/48. So df of a percolation cluster is equal to 2 minus delta magnetic equal to 91/48. Right. And that was the end of my second talk. So let's go now to the third talk. And the third talk is harvesting more results. And fortunately, it's a little bit shorter than the second one, so there's a reasonable chance that I will get to the end. Okay, so now I'm going to talk about a problem of combinatorics, which is that of Hamiltonian circuits and walks on regular two-dimensional lattices. I'm going to show how the Coulomb gas construction can be extended to that case, and I'm going to derive for you a range of critical exponents. Let's look a little bit again on the OM model, on the hexagonal lattice. Recall that it was defined, and this hand here is kind of stupid. I have to ask the technician how to take that away anyway. So it was defined by the following vertices. I give a weight t to the empty vertex and a weight 1 to each of these vertices where there's a loop coming through. And then, of course, there's a weight n per loop. And here I have drawn the phase diagram. So remember that there were these two regions for g, g between 0 and 1, and g between 1 and 2, which gave the same value of n, but which was expected to reside at different values of t, which this should be capital T, and this should be translated from French to English, I'm sorry. So there's this curve here, which is actually known from an exact solution, which describes exactly what critical model we are talking about. So there's a formula for this guy here, which is c squared equals 2 plus minus square root 2 minus n, which was first found by Nienhaus. And I didn't derive for you the critical exponent, which is conjugate to this temperature, but if you do derive it, you will find that this bottom branch here of the curve is renormalization group attractive, and the top one is renormalization group repulsive, so that is what those arrows indicate. Okay. It turns out, for simple reasons, that the partition function only depends on t squared, for the very simple reason that on a lattice with appropriate boundary condition, there's always an even number of voids. So this is bound to be symmetric when t goes to minus t. So if there's an RG flow going up like this, it means that there's also an RG flow going down here. So the line t equals 0 is a line of fixed points. I don't know yet if it's a line of critical fixed points, but that turns out to be the case. So that is the very model I'm interested in. I put t exactly equal to 0, and I want to see what that changes. So no voids are allowed. Okay? So I have loops on a hexagonal lattice which jointly come through all of the vertices of the hexagonal lattice exactly once. And if I take the limit of n goes to 0, there will just remain exactly one loop. And that will be a Hamiltonian cycle. So I'm setting out to solve that theory. So my partition function is defined as the sum of all graphs which are fully covering small n to the power big N, where big N is the number of circuits. I can also obtain Hamiltonian walks because you have seen here just how I could insert these defects. Suppose that I insert a pair of one-leg defects at two prescribed points. Well, then the n goes to 0 limit will mean that there is one single Hamiltonian walk filling out the lattice and going from one defect insertion point to the other.
Yes, I'm not sure Hamiltonian is the right word. In the lattice, is it not true that you're covering all the edges?
No. The model is this.
The relationship between T and N.
Yeah, okay, sorry.
Yeah, there's a relation between T and N if you want to sit on this critical manifold
Just
here.
to make it onto the slide.
No.
There it is.
But I'm going to talk for the next couple of minutes about only this line t equals 0.
Equals 0 should be.
Are you convinced that those are Hamiltonian walks then? Okay.
I was still on the square lattice.
Yeah, let's get back to the square lattice in a minute.
Yes.
Well,
How are you going to get t equals 0 from that equation over there by making n? You're going to have to make
n equals
complex.
-2, right?
Okay.
Yes. So there's a very singular point sitting down here at -2, which will sort of,
Right, that,
where this line will meet this line.
right. T equals 0 is n equals
-2.
n equals -2.
Right.
Okay. I can do it.
Okay, we have just seen in my second talk how these loop models in the case where I had t different from 0 mapped to a one-dimensional height model. What I mean by one-dimensional was that the height was just a scalar. Well, nothing prevents me from having a height which is a vector. So I have a model which lives in 2 dimensions, and to each point on the dual lattice I associate a vector which lives in 2 dimensions. Why do I need 2 dimensions? Well, I need...
Sorry, before you go on, is that a misprint or what? In other words, to get t equals 0, you need n equal to -2. You have n goes to...
No. Wait a minute. There seems to be a little bit of confusion here. Okay. So, a long time ago, people have known how to describe this thing. And that was the object of the results that I just gave you in say, the second talk, right? Now I'm going to talk about this line here, which I have just argumented is at least a line of fixed points. I don't know for sure yet that it's a critical theory, but I'm going to find out that it is. And so now I'm just constraining to this line here. So there's a third solution, which is just t equals to 0. So there is no voids, and I'm talking about Hamiltonian cycles and walks.
Between t and n on that line?
Yeah, t of n is equal to 0 for any n. it's just t equals 0, right? T equals 0.
Okay, so in other words, the old de Gennes correspondence was n equals 0 corresponding to polymers.
Right.
So, and n equals -2 was Gaussian. Okay.
That's true.
In
It's a
RG.
different curve.
Okay.
But I'm talking about a different curve.
You're
Forget this curve here. Forget everything which goes on up here. Just think about t equals to 0. So my model now is changed. This is no longer allowed. Loops are supposed to cover the whole lattice. Okay. And now I'm going to show that this model is going to give me a height model where the height is not a scalar anymore. It's a 2-dimensional vector. And how would I argue that? Well, the lattice is bipartite, right? So if I take here an even vertex and here an odd vertex, there are 3 things which can happen on an edge. Either the edge can be empty, or there can be an oriented loop going in one direction or in the other direction. So let me say that this thing here is associated with a height difference of A, where I don't know what A is. This is B, and this is C. And then let me look at what happens at any vertex. Well, at any vertex there is one oriented loop going through. So there is one A-type edge, there's one B-type edge, and there's one C-type edge. So if I go around here, I see that I've got H plus A, H plus A plus C, and H equals H plus A plus B plus C. So whatever these H, B, and C's are, they should add up to 0. So by symmetry, I just take them to be vectors going like that from the center out to the vertices of an equilateral triangle. And so since, of course, my normalization is not going to be important, let me just take them to be that. Let me now discuss another model before going on. So the other model comes with a nice drawing here. I call that the FPL2 model. FPL means fully packed loops, and 2 means that there are 2 different types of loops. So that is a model on the square lattice. So there are black loops now and green loops. And at every vertex, I have these 6 possible configurations, meaning that every vertex is visited by one black loop and one green loop. They never share the same edges, but they can cross. Black can cross green, but black cannot cross black. So if I disregard the green ones, and if I look on a configuration of a large lattice, it looks like this. So you see you have loops of all possible sizes, so there should be some chance of having a critical theory. The long loop here has length 1062 lattice spacings. And of course I have just, it's just an example of a long loop. So my partition function is now a weight for black loops, small nb, raised to the number of black loops, in green raised to the number of green loops. And I want to convince you that that now maps to a three-dimensional height model. What do I do? Well, the square lattice is also bipartite. So there are even and odd vertices. So now I should have black and green chalk. I don't. So let's do with white and red. That will make things look more Danish anyway. So there are 4 different configurations of an edge corresponding to the color of the loop living on that edge and its orientation. And I associate height differences A, B, C, and D. And if you go around a vertex, you'll see that A, B, C, and D should add up to 0 to have a consistent height mapping. So I can take them as pointing from the center to the vertices of a regular tetrahedron. So now we move to the second section. I want to adapt the Coulomb gas construction that we have seen in detail for a scalar height to the case of vector heights. And the first crucial point is to find out what to do with this compactification. So recall that before you had to identify phi, which was the continuum limit of this height field, with phi plus 2a. Well, now clearly it's going to be identifications with respect to lattices living in respectively 2 and 3 dimensions. How do I find out how to do that? Let me talk about the square lattice model. So there is this trick again, which is to look on states just having loops of the smallest possible length, which I'm going to use again. So suppose I have such a state, so black and green loops, well, they look a little bit yellowish, but still they're green. So they look like this in the unoriented loop representation. If I add orientations, such a particular state might look like this. This is what it looks like in terms of these edge labels A, B, C, and D. And on the dual lattice, I have these heights. So those are 4 equivalent representations, sort of. And so I see that a state like that is going to be microscopically flat. It's just small fluctuations around a constant height. So now I do the following. Well, I call that an ideal state. So there are 24 ideal states corresponding to the 4 permutations of A, B, C, and D around a vertex. So the idea is I can change one ideal state into another one by taking one color pair. Say I choose a vertex here and I choose A and D. And then I follow an AD, AD, AD loop around and I change A to D and D to A. I start doing that and then I do it all over the lattice and then my height will change gradually. And when I have done it everywhere, the average height will have changed a certain amount. And I'm going to embed that into 3-dimensional space, saying that I started here in 3-dimensional space and now I move along this edge here. It's not an abstract graph, it's actually embedded into 3 dimensions. And the position of each vertex represents the average height. Okay? So I do that, and then I start doing another color transposition. By color, I mean these labels A, B, C, and D. And then I start moving along another edge, and I find another point. And if you do that, well, the first time you have to do it, it takes you several weeks, because it's a bit complicated. Then you get clever, and then in the end you find out how to do it in 5 minutes. And so you find out that this will give you it will give you a covering of R3 with truncated octahedra,
Is
like
that,
this.
Well, atomic structure of a diamond crystal?
That is possible. And so now, as it turns out, this state here, I mean, there are only 24 different states, right? So this state here corresponds to something sitting elsewhere, which is the very same microscopic state. So I have to identify them. A fixed ideal state occurs infinitely many times in this ideal state graph. And that defines the lattice, which I will call the repeat lattice R, with respect to which I am going to have to compactify. And it turns out to be a face-centered cubic lattice with a cubic cell of edge length 4 in the normalization that I took. Of course, that won't impress you a lot, but it tells me exactly what to do. I should also say that for this other model here on the hexagonal lattice, which is only 2-dimensional, this here will be replaced just by a triangular lattice, or maybe a hexagonal lattice again. And then I think R is going to be a triangular lattice. But I can work all of that out by this kind of geometric computations. So what is that going to mean for the Liouville field theory, or the compactified boson field theory? Well, my height lives now in RD. Well, D, capital D was 2 for the 2-dimensional model, and 3 for the 3-dimensional model. Up to this R, this repeat lattice. And my electromagnetic charges are such that the magnetic charges, the height defects, live actually in this R, and the electric charges live in the dual lattice R star. So let's think specifically now about the model on the square lattice. Well, I guess I'll take the square lattice as an example. So there's going to be an elastic term in terms of these heights, which now have 3 components. So the indices for components in height space are called, well, they're Greek letters. By rotational invariance, I can only have scalar products. So there's an elastic tensor here, a 3x3 tensor that I need to fix, and it's constrained by various symmetries. Because if I change all A's into B's, and if I take the convention that alternations of A and B define the black loops, that's just kind of a symmetry. It leaves NB unchanged. So I have to go through a little bit of symmetry work here, and what comes out in the end is that there are only 3 non-zero coupling constants left, which I will call K11, K13, and K22. And with the choice of conventions that I have taken, they are going to couple to the height components in this particular way. So there's a certain amount of work going into that kind of identification. Of course, I can make this diagonal by changing the basis for H. I could also have cheated. I could have chosen the right basis from the outset, but then you wouldn't have seen that. In general, there's this kind of complication. Okay, that was the elastic term. Now there's this boundary term. And now I see that something terrible is going on, because the scalar curvature has now the same symbol as this repeat lattice. So whenever it occurs without an argument, it's the repeat lattice, and when there's an argument, it's the scalar curvature. But in any case, what I do is that black loops are alternations of A and B, and green loops are alternations of C and D. And this SB here was actually measuring the height difference between the two extreme ends of the cylinder and had to do with loops that wind around. So if there's a black loop winding around, suppose this is black, it means that a little bit depending on exactly where I look, if I'm cutting between an even and an odd vertex or the other way around, that there's an A or an B here. So to give them the right weight, I have to have E naught times A equals pi EB, and E naught times B equals minus pi times EB, where I have used this parameterization for the weights of black and green loops. And so there's some solution to that. So now I have found the generalization of this electric charge E naught, which is a three-dimensional vector. So finally, there's the third term, the Liouville term, which is going to be the continuum limit of my microscopic vertex weights. Suppose I write as sigma 1 through 4 the colors around a vertex. Colors are A, B, C, and D's in some permutation. Then you can show that the microscopic height can actually be written in this neat way. And you can start Fourier analyzing it with respect to this lattice R to find out if it has a higher period, well, no, with respect to the lattice I, to find out if it has a higher periodicity than just the trivial one imposed by this repeat lattice. And it turns out again that these electric charges here should live in some sublattice of R star, the dual lattice, which is spanned by the next shortest vectors in R star. So now I have everything that I need. I only need to generalize the result coming from this compactified boson conformal field theory to vector charges. So if I take the basis where the coupling constant tensor is diagonal, in which case I will denote its elements not by capital K but by small g like I did in the previous case, then my crucial formula is this. And then I do the same thing that we just did in the scalar height case. I say that loop weights do not renormalize. So I take the most relevant, the renormalization group most relevant electric charges in this weight lattice here, and I claim that they should have dimension 2. That gives me exactly 3 constraints. That is very nice. And it exactly relates the 3 components of my coupling constant tensor to the 2 parameters E black and E green that define the weights of black and green loops. So at this point the theory is solved. And that is nice because that leaves me 13 minutes to tell you the results. So let me remind you that the 2-dimensional model here was called the FPL model, fully packed loops, and this doubly fully packed loop model on the square lattice is FPL2. So the central charge I can work out as before. You just see that instead of having 1 here, there is either a 2 or a 3 coming in. That is because I now have either 2 or 3 bosons. And there's a small correction coming here, and that correction comes directly from this boundary term, SB. So the central charge is given by this. Now if you remember my first talk, there was something special about central charges less than 1, right? In particular cases, they corresponded to these unitary minimal models. So why is the central charge now going above 1? Well, that is because these theories have extended symmetries. They have larger symmetries. in standard conformal field theory, there's some SU2 around. And it turns out that in this model and in this model, there's respectively SU3 and SU4 that can be made very precise, but I will refrain from doing so because it would take me too far afield. I can generalize these watermelon exponents now by inserting vector defects. So suppose, for example, suppose that I want to say something about Hamiltonian walks instead of Hamiltonian circuits and say on the square lattice. So I want two vertices and I want a directed Hamiltonian walk connecting the two. Let's say that this is black. And red is green, as you might have expected. There's going to be four edges coming out of this point here. So it's impossible to have a black line without also having a red line, actually. And then to occupy the rest, you can just have a standard black loop doing something like this. So the end result is that here I have got a defect which corresponds to an A, a C, an A and a B. So the sum of these guys here is not 0. It is equal to A minus B. So there's a vector defect here, and then there's the opposite vector defect up here. And those I can just insert into my formula to get these watermelon exponents for L strands going from one point to the other. I have complete formula, of course, for when I specify both the number of black and green strands, but just to keep things simple, I'll completely forget about green and put the loop weight of green equal to 1 so that I won't see green. And so the result is that on the hexagonal lattice, also known as the honeycomb lattice in physics, I'm afraid, delta L will take these values here, where you now see that there's a difference between L even and odd. They don't fit into the same formula. And the even formula was just exactly the same as you found in the one-dimensional height case, whereas for L odd, it changes. And the model on the square lattice has kind of the same structure, except that now there's yet another thing which differs for L odd. So those are kind of main results of this thing. And so now, if we were doing polymer physics or anything like that, then I would just finish with this last slide. And I would concentrate on the number of self-avoiding walks and polygons. Translation, self-avoiding walks, that would be Hamiltonian walks, at least in the limit n goes to 0. And polygons would be Hamiltonian circuits. And so there are some general arguments that the number of walks is supposed to go like some constant mu to the power L. L is the length times length power gamma minus 1. Whereas the number of polygons is going like mu to the LL to the minus mu times D. D is the dimension of space here, 2. Mu is some number that you can't find by conformal field theory because it's non-universal in some sense. You can find it if you can solve these things exactly. But gamma and mu are critical exponents, and those you can find because by some standard scaling relations going back to the work of De Gennes, who has already been mentioned by Robert, they are related just to these watermelon exponents delta 1 and delta 2 in this way. So since I know delta 1, delta 2, I know gamma and I know mu. And so here are the results. Always for the limit where n goes to 0. So the limit where there's just a single circuit or a single walk on the lattice. And so now this is the summary of everything, right? So for the one-dimensional height case, I had these two solutions. There was this Nienhaus formula which disappeared, so that will be, so remember. Here, there's this point here, so that is self-avoiding walks with a lot of empty space, self-avoiding walks with little empty space, and self-avoiding walks with absolutely no empty space. And the first two here don't depend on the lattice, and this guy here comes in two versions, for the hexagonal lattice and for the square lattice. And so the results are these. So dilute means the uppermost branch, still dense means the middle branch, and this means the t equals 0, and this means t equals 0 but on the square lattice. So we have these exact results here for nu and gamma. And so you can actually convince yourself that gamma minus 1 tells you so you have a walk with two endpoints. So what's the probability that these endpoints are separated by a distance r in the limit where r is small compared to the length of the whole object, but large compared to the lattice spacing? Well, then I would expect P of r to go like r to gamma minus 1 from some scaling relations.
It's r to the minus eta, where eta is the usual critical exponent, going from gamma and nu.
Right, I think I'm saying the same thing here, if you apply scaling relations.
Eta.
I might be off by a factor of 2, I'm not.
Eta is 2 minus gamma over nu.
Maybe it's this. Maybe it's this, and maybe this relation here misses a nu somewhere. Maybe it's 1 over nu or something like that. So in any case, for the two most interesting models that you see here, you see that for this model here on the honeycomb lattice, the two endpoints don't interact. The probability distribution is flat. Whereas here, the probability distribution goes like r to the 5 over 56, meaning that there's an extremely weak repulsion between chain ends. So you see, it's very crucial to say on which lattice you live to have this kind of results. And there are 3 minutes left for questions, because I believe I'm done now.
So in contrast to normal applications of conformal algebra, here you have lattice dependence of exponents.
Right.
Yeah.
Yes.
I mean, for the ferromagnetic case, you normally
Yes.
have lattice universality.
Right.
Here you-
But with these
And
fully
so on.
tracked models, that's not so surprising.
No, Alan is not so as surprised as I would have hoped him to be. But of course, you see, the whole difference is that universality. Well, I mean, mathematicians would never like any such notion anyway. But universality, for what it means in physics, is that the universality class, the critical exponents, are fixed by the symmetries of the model, and that symmetry, I guess, should include the dimension of the order parameter, which is 2-dimensional here and 3-dimensional here. So from that point of view, just as soon as I have this height mapping and see that it lives in respectively 2 and 3 dimensions, I can start suspecting that it's going to have some bearing on the critical exponents, and that they are going to be different.
As contrasted with Nienhaus,
Yes.
sort of analysis, which was
Right.
absolute.
So I mean, you can get out from this machine that I'm still learning about saying these. What you can do is you can work out what these exponents are for the number of these self-avoiding walks and polygons.
Right.
I mean, are there other sort of obvious combinatorial trails round the lattice, so to speak, that you can do similar enumerations for?
Yes.
More complicated things. I suppose that if you think of a polygon as, for example, as being two regular walk around in this lattice. If you ask about, say, three regular graphs on a subset of the lattice, could you say something about the number of those?
Three regular graphs. Well,
Do you mean,
I mean,
you mean
what we're getting out from this machine, which I'm going to say, I don't yet fully understand yet, is that it seems to be telling us what these exponents are for the number of these self-avoiding walks and self-avoiding polygons and things. I mean, a self-avoiding polygon, for example, is basically a graph that's going to go around and come back to where you started it. It's a cycle. Can you say, you know, how many of various other more complicated graphs there are?
well, if I understand correctly, your technique would be more like you specify a topology, which might be some fixed small graph.
yeah, I
And then you
specify.
allow that topology to be represented in the lattice by each edge of this fixed small graph is a self-avoiding walk in the lattice. And the different self-avoiding walks are supposed to be internally disjoint. Isn't that
Yes.
the point? That
Right.
it's not that you represent, you should not, I guess a graph theorist would say, what you're representing is things on the lattice that are homeomorphic to some particular simple structure.
There are some limitations of this approach. So I would not expect to be able to do anything if the graph isn't regular and planar. Or maybe using other techniques, but not exactly those, but using other techniques. At least as long as it's planar, I could do
we can
something.
get in your terminology, we can understand the self-avoiding walks because they are, well, subdivisions of a nice simple graph with a single edge. And we can get the polygons because they are subdivisions of a nice straightforward graph with
Or a
cycle.
loop,
Depending where you
yeah.
want to start, or you
Right.
if you want to do it that way. But anything much more complicated than that, things are going to get nasty. Subdivisions
Right.
of the technology seems to give us.
But you could,
There's another very important limitation, that is that all of these circuits here are self-avoiding. They don't cross. That is absolutely crucial for being able to redistribute out the loop weight in this local manner as these complex weighted terms. If I can't do that, this technology will break down also.
but for example, one thing that's not in the list that you've done, but maybe you could do, consider the complete graph on 4 vertices. Okay? Consider that topology. That topology can be embedded in the plane. Now, count the ways that you can have paths, 6 self-avoiding paths in the plane. 6 self-avoiding and internally mutually avoiding paths on the plane that together represent the topology of K4.
Right.
You could probably.
I have tried very hard to have 3 different types of circuits on the triangular lattice, so that every vertex on the triangular lattice is visited by a red and a blue and a green. Okay. And unfortunately, the results are slightly deceptive, because what happens is that the triangular lattice is not bipartite. And if I don't have something bipartite, there's a problem with defining these A, B, C's, and D's. So with a student, we have tried various other ways, and you can define some very nice models. Unfortunately, what will happen in the continuum limit is that the 3 bosons that you're supposed to use, I mean, let me say that again, that it's just going to be 3 decoupled bosons. So each loop, say a red loop in the continuum limit, does not see what the blue and the green are doing. That is what was really magic about this model here. That is that even though in the end I weighted green loops trivially so that you didn't see them in the model, the black loops knew very well that they were there. And they had their critical exponents take exotic values such as this, exactly because of that fact. But maybe there's some trick. I mean, what we found out is that on the 2 first lattices here, there's kind of only one natural way to define the problem. And on the triangular lattice, if I remember correctly, there were at least 3 natural ways of defining it, which were considerably more complicated. So maybe there's a 4th way that we simply didn't think of. I should also mention that this problem here solves the meander problem that you might know of. So the meander problem is you take 2 closed curves and you ask in how many topologically inequivalent ways can they intersect one another, given a prescribed number of intersection points. Well, that's not a regular lattice problem, but we have some technology for translating critical exponents. There's a formula called the KPZ formula. It's not Carter-Parisi-Zhang, it's Kniznik-Polyakov, Samologikov, which translate these critical exponents, the delta L, into their corresponding values on something which is not a regular lattice. And what you see here is that you have essentially 1 black and 1 green loop, sorry for the colors again, which intersect all the time. And so if you do a little bit of arguing, you'll find the exact asymptotics of that model by using these results here.
Is this what was done by Philippe Di Francesco a few years ago?
Yes.
And so that you get the same answer by a different method? Or is it?
No, I mean he used this work here.
Oh, I see, okay.
I mean, I guess I could have done so if I had knew the meander problem at that time, but I didn't know the problem.
But I remember the miracle of that work was 2 things, I mean, for a mathematician. First of all, you have this behavior mu to a power, I mean mu to the L to a power, and the dominant term, mu to the L, we have no idea what it is. Mm-hmm. It's a combinatorially defined problem, and the mu, we don't know what it is, but nevertheless you can say exactly what the subleading term, the L to the power, is.
Yeah,
and secondly,
that is, I can see why that is frustrating. Of course, there is some explanation why that is so in physics, because mu has kind of the role of the inverse of a critical temperature.
Non-universal.
Sorry, non-universal.
Non-universal.
Yes. And so you expect the critical temperature to move when you go from a lattice model to the continuum.
But in the meander problem is purely combinatorially defined.
Right.
So it's a little strange that there's this unknown mu there.
Yes.
And then the second thing that was totally crazy was the critical exponent wasn't rational.
That's because of this KPZ relation, which involves a square root.
There wasn't some, I don't know, it's square root of 145 in it or something crazy.
Right. Yes.
Well, it was quite striking.
But actually, I mean, you can. My observation that on a triangular lattice that things decouple, well, you can turn that into maybe another problem which will interest you. So you generalize the meander problem so that you now have curves of 3 different colors, okay, and you allow them. You allow only intersections where all of the 3 different intervene. And one thing that you don't allow is that let's see. So you would allow that a white comes in like this, or maybe that it does like this, But one thing you don't allow is that it goes like this, because then you could just pull it away. So you need the thing to be blocked at all vertices or somehow. So, I don't know. Something, right? And they are not allowed to cross elsewhere. So now here I'm already stuck. So that's a problem. So how many of these guys are there? Well, on the triangular lattice, well, you have these three bosons. Each of them count for central charge -2, so it's central charge -6 in total. You throw that into the KPZ formula, and I have already then the prediction for this problem. I need something to do the exact enumeration to check if nothing went wrong, but I suppose that wasn't the case. And I mean, you can take any number of curves like that, so you will get a horrible problem about topology, and all of those I claim should be solvable by.
But you can predict the sub-leading term in every case, but you don't, but
not the leading one.
Non-universal part.
That's
Right.
Yeah. Okay. I just want to know what the method will be.
So, in this, for example, for your FBL square, in usual conformal algebra, you have an operator algebra and fusion rules, and you work out the conformal grid and so forth. Do you get any interesting information from that in that case? In this case?
No, that hasn't been done in the same detail. Yeah, but I mean, there is still work that one could do. Yeah, so maybe you could contribute to that, I don't know.
Go eat.
Let's do so.